Alright everyone, let's get started. Today we'll be talking about two learning algorithms, the Perceptron learning algorithm and stochastic gradient descent. So just a, what happened here? Okay, I don't know what happened there. Okay, I don't know what happened there. Just a recap of last lecture. These are sort of the basic ingredients of supervised learning. You have a collection of training data. And here, for simplicity, we'll look at binary classification, where the let's see if this works. Yeah. Where the labels, the target labels y, are either +1 or -1. We are going to choose a model class. Here we're going to still stick with linear model classes, which basically means that the scoring function is a linear function of the input features x, possibly with a bias or offset term denoted by b. And by linear, simply, I mean that the function is a linear dot product, right? The scoring function is a linear dot product. We choose a loss function that quantifies how poorly our prediction is mismatched with the ground truth. For simplicity here, we're going to look at square loss, where the penalty is simply the square deviation of the prediction versus the ground truth. Given all that in the recipe, we then specify a learning objective, which is specified in this bottom one, where basically we want to minimize this loss function over our supervised training examples. And by minimize, I mean find the W and the V that minimizes this loss function, right? And this minimization problem is known as an optimization problem. And in this case, the learning algorithm, if you will, basically boils down to solving this optimization problem. So that's the basic recap of the last lecture, at least the learning objective part. Any questions on that? All right. Okay, I'm just going to. I'll just do it. Okay. So the other thing that we talked about in lecture last Thursday was overfitting, the bias-variance tradeoff, things like that. And so just as a quick recap, for any model class, and here for simplicity, we're looking at one-dimensional functions that are either linear, quadratic, or cubic. So the function class is the class of all linear functions in 1D, the class of all quadratic functions in 1D, or the class of all cubic functions in 1D. Then you can compute the bias-variance trade-off, or at least you can analyze the bias-variance trade-off over some distribution of training data by randomly sampling from the test distribution a subset of training data, training a model, looking at its predictions, repeating this process, and looking at the variance or the variability of the model that you learned, right? And so for subsampling 7 examples in this one-dimensional regression model, this is the variability you get for linear. This is the variability you get for quadratic. And this is the variability you get for cubic, right? And so even though the average prediction for cubic is very, very good, unfortunately, the variability is quite high. And so the bias-variance trade-off tells us that the loss of the test set, which is the thing that we ultimately care about, can be decomposed into the sum over the bias loss and the variance loss. And the bias loss is simply the deviation from this average prediction to the correct ground truth. And the variance loss, variance part of the loss, is simply the variability of the prediction, right? Which is denoted by these green lines. And so for this example, with training sets of size 7, it turns out that the quadratic model class actually optimizes the bias-variance trade-off and achieves the lowest total loss on the test set. Even though the cubic function fits the data better, we don't have enough training data. So we don't overfit. Any questions on that? Okay, and so this is the complete pipeline that we talked about by the end of last lecture. We have training data, we pick a model class, we pick a loss function, we solve this optimization problem. We may need to do some sort of validation to measure to get an approximation of the test error, we may need to do model selection. We'll talk about more about what model selection means in the upcoming lectures. And that's basically the entire pipeline for supervised learning. In today's lecture, we'll look at two actual learning algorithms. So two algorithms that try to solve some sort of learning objective, right? And they are the Perceptron algorithm and Stochastic radius. So we'll start with the Perceptron algorithm. The Perceptron algorithm is one of the earliest learning algorithms. It was first proposed in 1957 by Frank Rosenblatt, and you can see the machine they were using to implement the Perceptron algorithm right here. It's probably less powerful than a smartphone, but that's what they were doing. It's still a great algorithm, right? Even though it's such a classic. And the reason why is because it's fast. It's really fast to implement, fast to run. It has a clean mathematical analysis of its behavior. And so, oftentimes when you want to reason about the behavior of some sort of learning problem, you can reason about it through the context of running a perceptron algorithm on that learning problem. And it's also the precursor to neural nets, which have become so popular these days. Okay, so here's the perceptron learning algorithm for the linear binary classification model. So it's an iterative learning algorithm. And so we're going to look at the linear model class for classification, which basically means that we're going to take the sign of the raw score, right? So the training set is in the form of x1 pairs, where x is some feature vector, y is either +1 or -1. So this is for binary classification. So we're going to initialize our w and our b's to be 0. So this is a 0 vector, and this is a scalar that's set to 0. And then for every time step, for every iteration in the learning procedure, we will receive a sample from the training set. Right? So here we have n training examples. We're going to receive one of them. And in fact, you can receive the examples for the perceptron learning algorithm at least. You can receive the examples in some arbitrary order. Common one is random order. And then we'll make a prediction, right? If our model, our current version of the model, and here I'm suppressing the B for simplicity, equals the ground truth prediction, the ground truth label, excuse me, then we don't do anything, right? We just keep the same model parameters that we had before. If the prediction by a model does not match the target label, then we do an update. In particular, we do an update in the direction of the feature vector, input feature vector, with the sign with the label, right? So if the label is positive, we move in the positive direction of this feature vector. If the label is negative, we move in the negative direction of this feature vector. And that's the entire algorithm. Very simple.
The equation at the bottom, x and y are vectors.
All right, so y is a scalar, x and w are vectors, and b is a scalar. So you have, this is basically vector-vector addition multiplied by a scalar. Yes?
Since in F we're subtracting b, shouldn't y have like a different sign? Because if the label's positive, like increasing b moves like the hyperplane in the direction of w, but you want it to be the other direction.
Yes, you are correct. That is a typo. I'll just fix it right now. Ta-da. Thanks. Yeah, that was a typo. Okay, any other questions? Yes?
Why is it important that you go through the training set in a random order?
It's not random. It's in fact the order doesn't matter.
Okay.
Yeah.
But each element of x maps one on y.
I'm sorry.
Each xi maps one y, right?
Your training set is given in terms of pairs of x, comma y. Yes.
Yes. But so you're saying in the equation x is a vector, but y is a scalar. So y is like a vector of levels, right? A vector of yi, right?
Y is simply either plus 1 or minus 1. If I suppress the subscript, it simply means I'm not indexing over it.
Just maybe to be clear, in receive example, it would be x sub y I, y subscript I.
Right. I mean, then we can make the notation as complicated as we want. Then there's a question of okay, which I is it? You know, there's a level of simplicity versus complexity here. It is a vector and a scalar. It is a single training pair. Yes.
Is it works that it is sine omega transpose x plus b? Would that affect the final result?
If it's plus b or minus b, it really doesn't matter. They're mathematically equivalent. Okay. So to set aside about hyperplanes. A line is a one-dimensional hyperplane. A plane is a two-dimensional hyperplane. And we typically refer to hyperplanes more generically as some sort of separating plane through a d-dimensional space, right? And so this is actually defined by a w and a v. Right? So for one-dimensional case, you know, it is simply a one-dimensional line through a two-dimensional space, right? A two-dimensional plane through a three-dimensional space, etc. And so here, it's simply the W corresponds to the tangent normal to the line, or the hyperplane, and the B corresponds to the offset from the origin, right? If B was 0, then this hyperplane will intersect the origin. This is high-school geometry. And then we can think about distance from a point x to the line, or to the hyperplane. We use the same formula. And we often think about sign of distance in this class, which is simply not looking at the absolute value. Right? A linear model computes the unnormalized sign distance to the hyperplane. Right? So if you don't divide by the norm of w, you get the unnormalized distance. In particular, we don't take the absolute value either, so it's the unnormalized sign distance, right? So an example is over here, it's positive. The example is over here, it's negative. And the degree to which we think is positive or negative is correlated with the magnitude of the score, which corresponds to the distance from this point to the hyperplane. Okay, so now let's walk through a perceptual linear algorithm example. Here I'm not going to look at the offset term b for simplicity, so assume that b is just going to be 0. In general, of course, we do update b. And so we'll pick an example arbitrarily. Let's say this one. The first example is always misclassified because we're going to take the sign of 0, which is not positive 1 or negative 1. So then we'll make an update in the direction. So this is a positive example. We'll make an update in the direction of that feature vector that corresponds to that data point. And so we get this as a hyperplane, right? And this is the tangent normal, right? The tangent. So that's our model after one iteration. We pick another example arbitrarily. It's this one. It's classified correctly, so we don't make any updates. We'll pick another example. It's misclassified, right? It's on the positive side of the hyperplane, but it's supposed to be negative. It's a negative label. So then we make an update in the negative direction of this feature vector, And the feature vector is simply the direction, is simply the vector from the origin to this point. So then from this tangent normal, we make an update in this direction, which is basically the parallel vector of this vector. And this is our next model. And it now classifies that example correctly. That example is now on the negative side of the hyperplane. We go through another example. This one's classified correctly. It's on the negative side of the hyperplane. This one's on the positive side. This one is misclassified. It's a positive example. It's on the negative side of the hyperplane. So then we make an update in the direction of that example because it's a positive example. And now it classified it correctly. And now we can verify by just doing a for loop through all the examples that we've classified all the examples correctly and we're done. We will never make another update. Yes?
Is there any rules of thumb for assessing either stability or convergence rates?
There is, and we will talk about it in a few slides. Yeah. Okay, let's just do it again because, yes. Correct, and we'll see a second one right now. We'll see a second solution. So let's start again. Let's take an example arbitrarily. This one's misclassified. The first one's always misclassified. So you do an update in the negative direction of this example because it has a negative label. So now it's correctly classified. It's on the negative side of the hyperplane. Take another example. It's also correctly classified on the negative side of the hyperplane. This one's correct. This one's misclassified. So since it's a negative example, we move in the negative direction of the feature vector. It's still misclassified, but maybe we'll get back to it. This is correct. This is correct. Misclassified, we move in the positive direction. Misclassified, we move in the negative direction. Misclassified, move in the positive direction. And again, it's still misclassified, and now we're done, right? And so just to recap, and I'll get back to the point of multiple solutions in a bit. To recap, that's basically what's happening operationally. I guess we'll just change it right now so I don't forget. That's what's happening operationally in the pseudocode that you saw in the illustrated example. So, as was pointed out, there seems like there can be multiple solutions, and indeed, there are. There are an infinite number of solutions. Any of the solutions that sort of correctly classify all the examples is a potential solution, right? So I guess because there's a finite number of training examples, there's not actually an infinite number of solutions that the perceptron algorithm will converge to. But in principle, there are an infinite number of solutions. So convergence to a mistake-free hyperplane implies what the concept known as linearly separable. Okay? The training data is linearly separable if there exists a hyperplane that achieves 100% classification accuracy. Right? And now we can talk about things like stability by introducing another concept called the margin. So the margin is simply, and here again I'm suppressing the B for simplicity. It's simply the you find the W for any W that has zero classification error. You look at the distance you look at the closest distance of an example to the hyperplane, and that is given by this quantity right here. And you find the W that maximizes this distance, right? And that is known as the margin, right? So the margin is, a hyperplane. A hyperplane is this close to getting an example wrong, and this data set has this margin because there exists this hyperplane that can get this amount of stability. So, just to recap, classification problem is linear separable if there exists a W with perfect classification accuracy. It's called separable with margin gamma, and for a margin satisfying this formula. And linearly separable then basically means gamma is greater than 0. When gamma is really small, there are very few hyperpoints that can correctly separate the data. When gamma is very large, there are many, right? So it's easy to find. And in particular, one can prove this kind of analysis, which says that the mistake bound of the perceptron, so how many mistakes the perceptron makes while it's doing learning, so how many updates it needs to make, because it only does an update if it makes a mistake. So the mistake bound of the perceptron learning algorithm is upper bounded by r squared over gamma squared, where r is the size of the feature space, and gamma is the margin. I won't be going into the details of this proof. It's a very elegant proof. Multiple people have proposed different proofs. I like this one. And so if you're interested in some of the proof techniques that are being used, you can check out this link. Any questions on that? Okay. And oh yeah, this holds for any ordering of the training examples. Okay, of course, in the real world, most problems are in fact not linearly separable. And in the case where the data is not linearly separable, the perception algorithm may never converge. It will always make a mistake. It will always be making updates, and it will never actually converge, right? And so what do? We'll typically just use the validation set, right? So one example is early stopping. It's a very popular concept in the machine learning community. So we're going to run the perceptual learning algorithm on the training set. We're going to evaluate the accuracy of the current model on the test set, on a validation set. We terminate when the validation accuracy stops improving. That's basically what early stopping means. And people have done this for other learning algorithms as well. This is a very generic concept. It applies to other learning algorithms as well. Yes?
A question about the previous slide. The r squared over gamma squared. Does it make any sense to normalize all the x's so that it...
If you normalize the x's, the gammas also change, right? Because if you squish the data, the gammas also change. So it's the data as you're given, right? So the gamma and r are dependent on each other. So if you, in particular, if you scale down all the x's, the gamma correspondingly scales down. Right? Yes?
What does holds for any ordering? What does that mean?
The number of mistakes.
No, I mean ordering the training examples.
Yeah. So in the examples that I gave you, right? In these examples,
Oh, you mean the?
I picked some arbitrary ordering of the training examples to feed into the perceptual learning algorithm. Okay, so another concept is online learning versus batch learning, right? In online learning, we receive the training data as a stream, right? And we make we usually make incremental updates to our model as we receive the data in a stream. So perceptron learning is an instance of online learning, right? In batch learning, we're given all the data up front, right? So we're given all the training data up front, and then we do some learning on all the data given to us up front in a batch, right? Now, of course, you can convert any batch learning problem to an online learning problem by simply streaming the data to an online learning algorithm, right? So, people have often done a batch to online conversion because online learning algorithms have many desirable problems. So, just to reiterate that point, you can often use an online learning algorithm for batch learning by simply writing a for loop that streams the training data, right, to the online learning algorithm. Okay, so just a recap of the perceptron. It is one of the first machine learning algorithms. The benefits are that it's simple, it's fast, The drawbacks are that it may not be converged to a very good model, and we haven't talked about an objective function, right? So we spent all of the first lecture talking about this learning objective. I only gave you an algorithm that made updates. I didn't tell you what objective function it was actually optimizing. And so that's something that we need to discuss, and we'll do that later. Any questions about the perceptron algorithm? Yes?
Just to confirm, for all those, for the example that you gave, when you said you were suppressing the b value, you just meant that you were like computing the.
I was just forcing b to be 0.
Okay.
Yeah. In general, b is also a free variable in the same process, just for simplicity of the illustration.
Sure.
Okay, so now let's talk about stochastic gradient descent, which is the predominant learning algorithm people use these days. It's used to train everything from support vector machines to logistic regression to deep neural nets. So let's go back to optimizing learning objectives. So now we're going to talk about this loss function, this learning objective is built on top of this loss function, and we spent almost the entire lecture on Thursday talking about, and let's actually try to optimize this problem. To solve this problem, we need an optimization algorithm. The most straightforward one is called gradient descent, and it's exactly what it sounds like. Right? For this lecture, we'll stick with L being squared loss. We'll talk about other types of loss functions on Thursday. So just a recap of gradient derivation for squared loss. If we want to take the derivative or the gradient of the loss function with respect to w, which is one of our model parameters, then I'm going to write out the loss function as the sum over all the training examples, right? By linearity and differentiation, we can move the gradient operator inside the summation. We invoke the definition of our loss, which is a squared loss, and then we apply the chain rule. And so we get something that looks like this. And so now the gradient operator is on the model class, the score of the model, of the linear model. And then we invoke the definition of a linear model, and we get something that looks like this. All right, so this is the gradient of the learning objective with respect to W. And of course, it gets more complicated for other loss functions, other model classes, but this is sort of all the ingredients you need to do gradient descent. It should be fairly straightforward. This is essentially a first year calculus. And so here's the gradient descent algorithm. We initialize our parameters. Let's say 0. And then we do an update where we move in the negative direction, because since we're minimizing this loss function, we're going to move in the negative direction of the gradient. So we compute the gradient with respect to the current model parameters. We then make an update in the negative direction, and then we have this step size right here. And that's the entire algorithm. You have to, of course, pick the step size, and I'll talk about that in detail. But that's the entire algorithm. We simply look at where we are in the energy in the loss function landscape, and we take a step in the steepest descent direction to minimize this loss function. And we iteratively do this until we converge to some model parameters with a low loss. That's it. Any questions? Okay, so now let's talk about the step size. Okay? So how do we choose the step size? And so for simplicity, let's look at a very simple loss function on one example and one feature. Right? So this is a one-dimensional loss function, squared loss. On one training example, so the gradient looks like this. So I'm plotting the loss function as a function of this one-dimensional w. And suppose we're here, right, at w equals 0. And this is the gradient, right? And we're going to set the step size to be 1. You can do the math, we'll end up over here, right? And then the gradient now points in this direction. And we're going to still keep the step size as 1. We're going to do an update. We'll go over here. And then we'll update again. We'll go over here. So what's happening is that this learning procedure will oscillate infinitely. Right? And this is because the step size is too large. Right? If the step size is too large, the learning algorithm, the gradient descent learning algorithm, may not converge. And in practice, in my experience, if it's too large, it definitely will converge. Okay, so let's choose a step size much smaller, right? We got scared by the first example. Let's choose a step size that's way smaller. So then we're going to do an update, do an update, do an update, do an update. The problem here, of course, is that it's going to take a really, really long time for us to converge to the optimal W, which with minimum loss, which is right here. So this step size, although it will guarantee convergence to a good W, it's too small, right? And it'll take too long. You might be running gradient descent on your computer for a very, very long time. And so here is a few examples of different step sizes for a very simple learning problem that I just tried with gradient descent. Note that the y-axis, the absolute numbers, are not meaningful. The only thing that you should focus on is the relative difference in the magnitudes, right? And so for step size 0.001, after 200 iterations of learning, we're here, right? For step size 0.01, this is what we get. For step size 0.1, this is what we get. And then for step size 0.5, we actually diverge. And in this example, you can verify that if I choose a step size greater than 1, we will diverge. And so what I hope you can take away from this is that you want the step size to be as large as possible without diverging. Right? In practice, knowing what the step size limit is that will cause you to diverge is a little bit of an art, a little bit of trial and error. But this sort of is the concept behind it. Another issue that I want to talk about is that when you reason about this, you want to reason about it in a way that's scale invariant, right? Suppose we are updating two learning problems, so W and a W for two different, we're updating our model, considering updating our model for two different types of learning objectives, L and L hat. And suppose that L hat is simply L scaled by 1,000. So how are the two step sizes related? Well, if you want the two gradient updates to have the same behavior, right? You want this step size to just be 1,000 times smaller than this step size. And the W you learn is exactly the same. Right? So here's some practical rules of thumb, right? People often divide the loss function by the number of examples, right? So you normalize the loss function by the number of examples. You start with a large step size, and then if the loss plateaus, you scale it down, right? So you divide by, let's say, a factor of 2 or 10. You can also use more advanced optimization methods. There are methods that do these types of adaptive step sizes automatically. The step size must decrease over time to guarantee convergence to the global optimum. You cannot use this fixed step size. If you use a fixed step size, it will only guarantee convergence to an approximate global optimum. And in practice, of course, although you can think about some of these concepts in the homework, in practice, the majority of the time when you use machine learning, these gradient descent, differentiation, and step size tools will just be provided for you, in various machine learning packages. But it's important to understand the principles that govern sort of why people do this in order to understand, in order to be able to use these packages reliably. Okay, another concept that I want to introduce, and this is probably something that most of you, or many of you are already familiar with, is one of convexity, right? A function, f of x here, and here I'm just using f generically, is convex if you look at any 2 points in that function, you draw a line, a linear function between those 2 points, the actual function sits beneath that linear function, right? So as illustrated here. That's essentially the definition of convexity. The function I drew up there is not convex, right? It doesn't satisfy this property. For convex functions, it's easy to, relatively speaking, it's easy to find the global optimum. Right? So if your learning objective, that sum of losses, is convex, then you have hope to find the global optimum W, right? W and B. Okay. A convex function is known as strictly convex if the difference, right? The difference between this line and the actual function is always not negative. And for this function, right, so if you took the gradient, right, the gradient is actually a locally linear extrapolation of the function at this point, right, often represented in this form, right, so at this point, you know, plus a local linear extrapolation. The actual function, for convex functions, the actual function always sits above the locally linear extrapolation. That's another definition of convexity. So when you have a convex loss function and a convex learning objective, and you're minimizing that, all local optima are global optima. Right? If a function is strictly convex, it has a unique global optimum. And almost all the standard learning objectives that we're going to talk about in class give rise to a convex learning objective. Sometimes the learning objective ends up being non-convex because we use a nonlinear model class, such as deep neural nets. But if you use a linear model class, then you get a convex learning objective, which means the gradient descent will always find you the global optimal solution. Any questions on that? Okay, so let's say our loss function is convex. So how many iterations do we need to do gradient descent in order to get a W that is within epsilon of the global optimal W? So this is one way of analyzing convergence, right? So there's a concept called Lipschitz, which is the smoothness of the function. So if the difference between L of A and L of B is less than because there's some constant rho times the distance between A and B, then this function L, for all A and B, then this function L is considered rho Lipschitz. And for Lipschitz functions, then you need 1 over epsilon squared iterations to get within epsilon of the optimal solution. If the function is called rho smooth, right, which means that the gradients are Lipschitz, right, then you need 1 over epsilon. Right? And this number is smaller than this number as epsilon goes to 0. Right? We are interested in the case where epsilon becomes really small. So if the function is Lipschitz smooth, you converge faster. And if the function is strongly convex, which means it's lower bounded by a quadratic, then you converge in log of 1 over epsilon, which is very, very fast. And if you're interested in the details of the analysis, we won't be going through that in this class. They're in one of the freely available textbooks linked to off the course website. And other places as well. So, in general, like based on this analysis, right, it takes an infinite amount of time to exactly reach the global optimum. And that is actually true. Right? In general, it takes an infinite amount of time if you want to exactly hit the global optimum. Right? But we don't really care, right? What we really care about is having a model that has low loss, right? It doesn't need to be the perfect model as long as it's good enough, right? So the question is, we want to know that we have a model that's here, rather than here. And we want to make that determination, without knowing how low you can go, right? You don't actually know the minimum loss that you can achieve. So, as you're doing gradient descent, you don't know how much further you can go. But in general, as long as we're close to the global optimal, we don't care. So, when to stop? So for the homeworks, you will be using a very simple stopping condition, which is simply a maximum number of iterations of gradient descent. In practice, and this is something that you're asked about conceptually in the homework, there are more intelligent ways of knowing when to stop gradient descent, right? So stop when progress is sufficiently small, right? What does that mean? That means as you're running gradient descent, the change in the loss function is becoming very small, right? For example, the relative reduction is less than 0.001. Stop after a pre-specified number of iterations. This is what we do in the homework. Stop when the validation error stops going down, right? This is also quite common. Also early stopping, right? This is an early stop. When you use machine learning packages, that are provided to us from various industry partners like Google, you can choose the stopping condition. Right? It's a bunch of flags that you can set. I generally prefer this one more often than not. That's by default, but it is a little sometimes tricky to reason about. Any questions? Okay. Oh, sorry.
I was wondering, why you prefer that. Are there certain cases where, looking at validation error is problematic?
When your training set is big enough, okay, there's a couple of reasons. You don't want to actually overuse your validation set, right? Because then you could overfit to your validation set. Right? So you want to be careful how much you use your validation set. You have to load multiple data sets in memory, right? So here, in order to measure this one, you have to hold the training set in memory. Here you have to hold the training set and the test set and validation set in memory. Those are two reasons. Yeah. Yes.
So, from what you're saying, does that mean that early stopping counts as partially fitting towards the validation set?
I'm sorry, what?
So does stopping when the validation error is low enough, stops going down? Does that mean that early stopping is partially fitting to the?
That's right. When you do early stopping, you run the risk of overfitting to the validation set. It is a lower risk than learning on the validation set because you're only measuring one number. You're not estimating the parameters of your model. You're just estimating a number, which is the loss. So you're only estimating one number, not a vector of numbers, which could be 1 million. And so the risk of overfitting is certainly small. But yeah, as you'll see in the Kaggle competition, mini project 1, there is a risk of overfitting to the validation set. Okay, so now I want to transition to stochastic gradient descent, and I want to do so by talking about the limitation of gradient descent, right? Gradient descent requires taking a full pass over the training data per iteration of gradient descent, right? So you actually have to do a summation, over all the data in order to compute the gradient, right? This is actually quite expensive if the training set is huge, right? So if we, do we need to do a full pass over the data before doing an update? right? So here it says, I'm not going to make a single update to my model until I've done a full pass over the training data, right? And I computed a gradient over every training example. And then I'll make an update. So stochastic gradient descent gets around that. And here's the sort of the thought process behind it. Suppose we have a loss function that decomposes additively, which is true for us, right? The learning objective decomposes additively per training example, right? So we have a loss function that decomposes additively. You can rewrite this as an expectation over the individual losses over the training examples, where the expectation is taken over uniform randomness over the training set, right? So these two quantities are equivalent if the training examples if you're specifying uniform distribution of the training examples. And so the gradient of our total loss function over all the examples, you can now write that as the gradient of the expected value of the loss of individual examples. And again, by linearity of differentiation, it's equal to the expected value of the gradient of an individual example. Right? And so, okay, this is actually, so if this is what we're optimizing, right? Then, maybe it suffices to take a random update, right? So we're going to select a training example at random, right? And then compute the gradient of that loss function on that single training example, and we're going to update. The expected value of this gradient is exactly the gradient over the entire loss function. So this is a noisier, so we're introducing noise to the gradient estimate, and the trade-off is we can make an update after only looking at one example, rather than having to look at a billion. Right. So that's the stochastic gradient descent. And it is also an instance of an online learning algorithm, because you're streaming training data to the algorithm. Any questions? Yes?
So in the homework, we use this epic scheme where you're going through reorganize the data into some random list. That's doing the same thing as this.
So in practice, we typically just shuffle the data, right, and then do a full loop over it. You're supposed to, the theory as I presented it here suggests that you should sample with replacement, right? For a large enough training set, the difference there is fairly minimal. So you typically just shuffle and then just loop through the data. There is other theory that tells you that that's okay. But for simplicity of presenting the concepts, I'm not talking about that because those are mathematically more involved. This is a much cleaner sort of mathematical insight. But even just shuffling and going through the data is okay. It adds more noise, right? Because as you shuffle, as you loop through most of the data, you lose the randomness of the last few training examples because they become deterministic. You have to go through these ones, right? So it actually adds more, adds another error in the gradient estimate, right? But there are people who have analyzed that and said that that's pretty small. But here I'm just presenting a very mathematically clean intuition, but this one suggests that you should sample the data points with replacement. Does that make sense? Yeah. Okay, so this is the stochastic gradient descent. It is the workhorse learning algorithm of almost all machine learning problems these days. In practice, of course, people don't just do a single example, right? They do what's called mini-batch SGD, right? So so we're gonna additively decompose the total loss function into batches of training examples. For example, 500 to 1,000 training examples are common numbers. So in sort of pure SGD, this is a single training example, right? For here, it's going to be like, say, 500. And then we're going to compute the loss over those 500 examples, compute the gradient, and do a gradient update, right? And we can leverage various vector operations to compute the gradient efficiently over 500,000 examples. And one of the reasons why people do this is it decreases the volatility of the gradient updates, right? If you average over more examples, the variance of the gradient updates decrease, right? And so the exact number you should use, 500 to 1,000, it's a little bit of an art, right? There's no good theory that tells you exactly how much you should use. So it's a little bit of a trial and error. These are some typical examples. Another benefit of SGD and mini-batch SGD is that it's easy to parallelize, right? You can, if you have a multi-core processor, you can shard your training data into multiple batches to gradient updates and then reconcile the gradient updates afterwards. So it's easy to parallelize. And this is the industry standard. Right? If you look at various Google and Facebook machine learning packages, underneath the hood, underneath all the bells and whistles, various deep learning, whatever, they're doing mini-batch SGD to optimize those model classes. Any questions? Yes?
So in terms of gradient updates to different mini batches, you mentioned that different cores work on different mini batches. So would they all add up their different gradient updates together?
Yeah, so some people have proposed, and this is beyond the scope of the course, but some people have proposed to simply allow the updates to overwrite each other. Right? And this is effective when the data is sparse, right? So, for example, if X was a sparse vector, like text, right? So for any given X, most of the feature values are 0, right? Because most words don't appear in most textual inputs. Then if X is sparse, then if you parallelize, you have a mini batch, it updates W on these features. This one updates W on these features, and you just write at the same time. The probability of a collision is very low, and you can just model the collision as extra noise in the whole process. Because you're already doing the noisy update, because you're sampling from the training set. And so you can model the collisions as just extra noise. And so, especially for the case where the X is sparse, you can just parallelize and overwrite. People have done other tricks as well. Right? Like things like what's called a parameter server, where you have a master-slave concept. If you know about distributed systems design, where the master collects gradient updates and then does a reconciliation if there's a conflict, and then pushes back. So there are different system designs. This is a topic of intense engineering and research at places like Google. Large-scale machine learning is a huge deal in industry, but it's sort of beyond the scope of this course. Okay. So, okay. One of the things about this plot was that it was generated by computing the loss over the entire training set, right? And that seems very, very expensive, right? One of the reasons why we're doing stochastic gradient descent is that we can avoid as much as possible doing a for loop over the entire training set in order to make a decision, right? And yet, if after every iteration of gradient descent or stochastic gradient descent, we ran another for loop over the training examples to compute the loss and check for convergence, that seems really expensive. So the most common trick is to not check every iteration, right? We can check every 1,000 iterations. You can also evaluate the loss on a subset of the training data. Right? As long as you have a subset of the training data that you think is representative, this may also work. But in general, do not, evaluate the loss over the entire training set, every iteration of gradient descent or stochastic gradient descent. The wall clock time of your learning algorithm will be super slow. Okay, so just to recap, stochastic gradient set. How I presented it conceptually here is that we're going to